Okay, well, so we've already got a long list of ways of fitting nonlinear functions. There's another whole family of methods called local regression. In fact, Rob, wasn't there a PhD thesis from Stanford on local regression?
I don't remember.
Rob's PhD thesis was called Local Likelihood and was an extension of these local regression ideas to a whole range of problems, and it's still used widely today.
I wouldn't say widely.
You're too modest, Rob. So here we have, we're not going to go in great detail into local regression, but I'll just give you the idea. Here we have some data, and we've got a region over here where we fit a linear function just to the data in this region. The points in the region are the orange points, right? So it's a local set of points. And so we locally fit a linear function. And in fact, we fit it by weighted least squares, and the weights are given by the heights of this kernel here, right? So the highest weights are given to points at the target point, which is where this orange dot is, and then the weights die down as we move away, okay? And from doing all that whole linear function, you'll just get one fitted value at this point over here. But then the idea is that you slide the target point along, and as you slide it along, the whole region slides along. So here we see the target point at this point over here. There's the weighting function. The orange points have moved, right? So we fit in locally at this region over here. We fit a linear function, and the fitted value is taken to be this orange point here at the target point. And so as we slide the region along, or the target point along, this whole system slides along, and we fit different linear functions. And that traces out the orange curve over here. And the reason we like to fit locally linear, as you might think, why don't we just fit a local constant or like a moving average, is that it does much better, for example, at the boundaries. It gives you a much better extrapolation at the boundaries. So this is called local regression, and it's a very popular way of fitting nonlinear functions, but just focusing locally on the data. Turns out,
it's probably fair to say that Loess and cubic splines or cubic smoothing splines are probably the two best ways of doing smoothing. And if you set the degrees of freedom about to be equal, roughly, they look pretty similar too in general. Would you agree?
That's right.
So either one of these is a good choice.
So as Rob says, Loess is the function in R for fitting this local regression, and we'll play with that a little bit in the lab, and you'll see it's very easy to use. So we're not going to say anything much more about local regression, but the concept of local regression is important. You can read more about it in the book and in our other book, Elements of Statistical Learning, and you'll see it's actually a very rich area and allows you to do lots of flexible things. Okay, the final topic, generalized additive models. So the general idea here is that you're going to fit nonlinear functions in a bunch of variables at the same time. But the additive in the name means that you're going to retain the additivity of linear models. And the reason that's attractive is because it leads to interpretable models. So here our model for y is an additive function of the different x's. Right? So we've got a function of x1, a function of x2, and a function of xp. These are our different variables in the model. And once you fit this model, you can plot the different contributions to the fitted model. So if the first variable is here, we've got a nonlinear function of year, and then we've got a nonlinear function of age. And the third variable in this case, there were three variables, was education, and that was a factor variable. And so there, a piecewise constant function is a natural thing to fit, one constant for each of the levels. But the point is the additive model gives you a picture that you can look at and appreciate the contributions of each of the variables to the composite model. Okay? And so the technology is about fitting nonlinear functions of several variables in this additive form. So you can fit a generalized additive model very easily using some of the earlier tools, for example, natural splines. So it's as simple as this. Let's suppose we want to fit an additive model in year and age. we can just have a call to linear model, LM, right? And we give it two terms. We've got the response wage. We have a natural spline in year with 5 degrees of freedom, plus a natural spline in age with 5 degrees of freedom. Oh, sorry, plus education. So that's the previous term here. Education is already a factor variable, so it will automatically fit the piecewise constant function. Okay? And that'll do it for you. As we said earlier, the coefficients that you end up, because this term natural spline in year, degrees of freedom equals 5, will actually generate a basis matrix for doing natural cubic splines. So that's a matrix of x's, contributions to the model matrix, and each one of them is going to get a coefficient. But we're not interested in the separate coefficients. We're interested in the overall function that it fits. So it's a fitted function, or this part of it, that for each part of it that's interesting. So this previous plot here was produced by plot.gam. If you try to plot this model, which is fit by LM, by just using the generic function plot, it'll make a plot that for linear models, which is not going to give you the right plot. But if you use plot.gam, it'll treat it as an additive model and plot a plot that looks very much like the one in the previous slide, focusing on the functions rather than the residuals and whatever the linear model plot does. So of course with generalized additive models you can mix terms, so you can have some terms linear, some nonlinear, and you can use, for example, the ANOVA function to compare models and test whether a term should be linear or nonlinear. You can also use other methods for smoothing. So for example, here we use GAM to fit the model because in the first variable we want a smoothing spline in year. So there we use the symbol S to tell GAM that it wants to use a smoothing spline with 5 degrees of freedom. And just to be interesting, the second term we want to fit with low S. So there the shortcut is LO in age, and there we specify the width of the window, the local window, by something called a span, which is the fraction of the data in the window, and then plus education. So that's like a fully blown generalized additive model. GAMs are additive, which means there aren't interactions in the model. Now you can put low order interactions in by just including them in a natural way. And there's several ways of doing that. You do get things called bivariate smoothers that take several variables, 2 or more variables. Or you can put in interactions in other forms. For example, this is a way you can fit a bivariate function in age and year using natural splines. It creates a tensor product of the two sets of bases and result in a bivariate function. So this is somewhat more detailed, but you can do this. And again, you can look, I don't think you'll see details in the current book, but in Elements of Statistical Learning, you can certainly see about doing things like this. You can fit GAM models for classification. It's the same idea. Here we fit in the logit of the probability as an additive model. And in this case, when you do a plot, it'll plot the contributions to the logit, right? Because the fitted probabilities are not additive in the functions, but the logit is additive. And so there we get the logit. This was actually fit using the following GAM expression to call to GAM. So there's our binary response. We ask for a linear term in year, a smooth term in age, fit by a smoothing spline with 5 degrees of freedom, and then the education term. And we tell GAM the family is binomial, so that's just like GLM, we tell the family was binomial, and it knows to fit the logistic regression model. Interesting to see the standard error bands for the linear function. It's giving you a standard errors for the slope. There's no intercept in these terms, they're all centered at 0. So the slope is of interest here. And of course, a standard error for a slope is going to be like a cone-shaped bow tie kind of standard error band. So that's a generalized additive model. Okay. Well, so that's it. That's a whole collection of tools you have for fitting nonlinear functions. Some of them you can fit directly using LM and GLM, and for the more sophisticated ones, you use the GAM package in R. There's also a package called MGCV, which is another package that has GAM models in it. Also using smoothing splines, slightly different approach to what we take, but you can use those as well. So you have plenty of tools at your disposal.
In our next section, I think we're going to talk about tree-based methods, which are nonlinearities as well, but involving more than one variable, the interactions between variables. So it's a good way of finding nonlinearities, but of variables in combination. So we'll talk about things like CART and other tree-based methods for nonlinearities.